Good morning. My name's Simon Jones. I'm Engineering Manager at GEA Searle. I'm going to be talking to you today about the research and development work we've completed around our new range of gas coolers, and then passing you over to my colleague Sean Armitage, who will describe how that's translated into a new product range. Okay, first of all, for those of you who aren't familiar with GEA Searle, we've been designing and manufacturing heat exchangers in the UK now for over 90 years. We're located in Fareham, between Portsmouth and Southampton. There's a picture of our site at the top corner of the slide there. For many years in the refrigeration industry, we've worked with people out there today and many who aren't here today on system innovations, and always tried to align with what the industry are trying to achieve and try to work with the industry for better technology. So we certainly like to think we've embraced the re-emergence of CO2 as a refrigerant. We've worked with customers on collaborations dating back to 1997. And as part of our innovation strategy over the last couple of years, we've decided to focus on natural refrigerants, natural refrigeration. So we initiated the project with Brunel University approximately 2 years ago to develop this technology. Okay, very quickly, we're all here today because we have an interest in CO2 as a refrigerant. I don't need to tell you about the environmental credentials. Sometimes it's overlooked what a good working fluid it is, very high thermal capacity. There are a number of different ways to work with CO2 as a refrigerant. Direct cycle, otherwise known as transcritical, secondary or cascade. I'm only going to be talking to you about direct cycle today because that's where the gas cooler is applied. A common type of direct cycle is the booster system, commonly used in commercial refrigeration applications in the UK and across Europe, I believe, which utilises appropriate compressor technology, which our colleagues from GEA will be talking to you about shortly, to improve the compression ratios and achieve the maximum system efficiency, which really shows how hard everybody's working to make CO2 work as a fluid and have an efficient system. Okay, so very quickly, what is a gas cooler? It performs the function of a condenser when the ambients are low, approximately 24-25 degrees C. As the ambient temperature increases, it pushes the fluid into the supercritical phase. So condensation is no longer possible when you get to the supercritical phase, as can be seen in the pressure enthalpy diagram on the left there. And therefore, the fluid goes in as a gas, it's discharged from the compressor as a gas, and the fluid properties progressively change, and it leaves as a mixed fluid, if you like. So, in summary, condensation is no longer possible because heat rejection is taking place in the supercritical fluid region. Therefore, it's commonly known as the gas region, so it could be said we're completing gas cooling, hence the product's called a gas cooler. Now, control of the operating system between subcritical and supercritical is managed by a valve such as the Danfoss ICMT or the ICMTS, which they'll be speaking to you about later, I'm sure, which works off a control algorithm to ensure the system's always working at the maximum efficiency. Now, with operating pressures above 100 bar and inlet temperatures well above 100 degrees C, a conventional heat exchanger isn't the best bet, and the construction of the heat exchanger needs special consideration. Okay, so in summary, a more detailed pressure enthalpy here. Typical operating condition, you'd be entering the gas cooler at around about 120 degrees C, trying to leave the gas cooler approximately 34 degrees C if you had a 32 degrees C air on. So that means we've got an approach temperature, as we call it, of 2K, which is very tight, you would say, which is why often you need a different style of heat exchanger, a lot more surface to achieve those very tight temperature differences. So, knowing what a gas cooler is, part of our strategy, we wanted to work on improving the gas cooler design and develop a product specifically for the application. So with Brunel, we had three major objectives. The first of which was to improve our understanding of the transcritical refrigeration cycle. We don't think it's enough to simply sell a component. We want to be able to work with system designers and part configurators to ensure that the customer's got the right product and be able to support that product when it's out in the field. We also wanted to optimize the design of the heat exchanger specifically for use with a CO2. As I described earlier, the operating characteristics are different to that of a conventional system, therefore a standard heat exchanger isn't appropriate. And perhaps most critically, we wanted to develop a mathematical model to use as the engine behind a product selection program so people could select our product. Okay, so the first stage of this project, of course, is to have a test facility. This is the test facility at Brunel. You can see the gas cooler at the top there. I won't go into it in too much detail because Danfoss and Frigido will be able to speak about it better than I. But you can see the high temperature and the low temperature compressors separated, and the ICMT valve there, which is used to control the operation of the gas cooler. At the end of the seminar today, we will have an opportunity to take groups around and actually look at the systems here at Brunel. And I'm sure you'll agree there's nothing better than tracing some pipes around. So this is another graphic of the test facility. It doesn't quite look like you'd normally see in a refrigeration application or in a refrigeration installation. It's because it is a test facility. You can see there that we've got, no red light. We've got these glycol tanks here, which can allow us to vary the load that the chillers and the gas coolers are operating at. We are controlling the temperature and the humidity, therefore the loading going onto the display cases we have. This allowed us to test the gas cooler in every extreme of temperature and application we could think of. We wanted to be able to ensure that the product longevity and operation would align with the customer's expectations throughout its life cycle. So this follows on to the gas cooler. It doesn't look like you would expect to see on the top of a supermarket. And that's because we wanted to be able to increase these temperatures up as high as 40 degrees C air inlet temperature, so for the peaks of summer in some parts of Europe, not in the UK, unfortunately. So we were doing the opposite of what you might expect to see, and that's recycling the hot air from the air off face of the gas cooler. So we calibrated this at the GEA Searle wind tunnels to ensure that those extra fans weren't going to have any effect on the airflow over the coil. We also did have some heater elements there so that in the summer months we could take it even higher as required. One of the big advantages of this test setup was that we could change the coils in there. So in this case, we were measuring with a 2, 3 or a 4 row deep coil, and in some cases, as the analysis was being completed, we could take the coils away, modify them, change them, possibly manufacture them again, and put them back in. It also allows a lot of future opportunities, and although this project's coming to an end, Brunel will still be using a gas cooler in their test facility, and as GEA continues to advance its tube fin configurations, we can then put the coils back in here and see how they're operating. So this is a graphic of what you'll be able to see later on. You can see we've got quite literally hundreds of temperature probes along every single circuit at regular intervals. Every couple of 100 millimeters, we're measuring the temperature to understand the temperature distribution across the gas cooler. This is actually quite an early photo here, so it just has 2 pressure transducers in there. Later on in the project, we actually installed another 4 pressure transducers, so on the inlet pipework, at the top of the headers, and after the header manifolds. This is to ensure we had a complete understanding of the pressure drop characteristics of the working fluid through the gas cooler. We also installed a UV camera so we could visualize the temperature distribution across the gas cooler. And we had accelerometers, which, as you can understand, they have a working fluid potentially going from 120 to 34 degrees C. There's a lot of different expansion and contraction going on within that coil block. And to ensure the coil block wasn't damaged in any way, we measured with accelerometers the movement of the coil. Okay, in addition to the testing, we were able to complete some CFD analysis with the university's help. Now, at GEA, CFD is sometimes referred to as colourful for directors. In this case, it wasn't. We were getting as much out of CFD as we possibly could. So as you can see, the temperature distribution or the air distribution across the coil block was enabling us to optimise the tube geometry within the coil, ensure we're using as much surface as possible, and ultimately allow us to optimise our coil design. This is a small selection of the test results. The gas cooler's been running for about 18 months, so there's too many test results to possibly go through them all. But it can be seen that both in the condenser mode, you would get a significant amount of de-superheating occurring as the fluid's entering the gas cooler. And in gas cooler mode, you can see that you're getting up to 80% temperature drop within the first few meters of the coil. So on the x-axis here, This is the meters from the inlet, the distance from the inlet of each circuit going through the coil, and the y-axis is the temperature drop. Now, knowing that you get such significant temperature drop on the first few circuits of the coil, we could then use the CFD to try to optimize these coils. So those of you who are familiar with our gas cooler product already will be aware that we've got this horizontal split in there. Now, we put that in there based upon our experience over the years working with steam coils and understanding that large temperature differences could pass some of that heat down to the tubes where you don't want it to be. What we didn't fully appreciate was the effect this was happening on the capacity. We have now learned that it has a 7% performance effect on the capacity of the gas cooler, which can now be incorporated into our product, and you'll see from the selections in the product selector. In addition to this, and this is completely novel, this is new to GEA Searle or anybody else, we've decided to put a vertical slit in here to stop any temperature being passed along to the second tube within the circuit. This increases the capacity anywhere between 2 and 4% depending on the operating conditions. This is completely unique to us. Okay, so having now optimized the heat exchanger for the application, as described, we wanted to have a better understanding of the application and the operation. Now, due to the possibilities for far greater temperature differences within the gas cooler, which can be as much as 2 to 3 times that of a conventional refrigerant, it can be preferable to reduce the airflow and increase the number of tube rows deep. So for a conventional condenser, perhaps where you've got 3 fans deep, so you've got higher cost in the fans, more surface, more energy in the production of the gas cooler, we can reduce that down to possibly 1 fan with 6 tube rows deep. So the total carbon footprint within the supply chain is reduced for the end users, as well as just the energy efficiency in operation. So the relationship between air volume and capacity is also dissimilar to that as a conventional HCFC. For a conventional system, if you were to increase the air volume by, say, 50%, that would increase the capacity potentially by 25%. This isn't the case with a gas cooler. We know that that relationship is actually quite different, and you will see the end use of that out of our selection program. The final aspect of the project was to develop this mathematical model to be used in the product selector, and this was developed by Dr. Yunting Gi and had been extensively calibrated against 18 months of capacity testing as well as CFD analysis. It considers a cross-counterflow operation of the working fluids. The fluid properties are also continuously adjusted as it's doing these calculations through an iterative process. Because the fluid's changing from 120 down to the mid-30 degrees, the properties of those fluids change considerably, and you need to consider that in the design and of the heat exchanger. Okay, so now that we had the mathematical model developed, we wanted to build that into our product selector so that all of our efforts could be translated out into a field. And I'll pass you over to my colleague, Sean Armitage, who will describe how that works.
Thank you very much, Simon. Okay, got it. First of all, I'd like to thank Brunel University, Simon Jones and Nick Atkins from the R&D at Searle for presenting us with a very good product for the future. I'm going to talk about the features of the product, a gas cooler, 4 fan modules, modular design throughout. We have a unit that goes from 1.2 metres through to 12 metres long. We're selecting gas coolers up to 700 kilowatts, from 15 dBA to 72 dBA at 10 metres. The unit is based on our standard RF air-cooled condensers. We're utilising a single-piece side plate. This goes up to 12 metres long. It gives us tremendous strength. This product has got to be shipped all over the world. I've already had people lifting it up with small forklifts in the centre. We get 1 millimetre deflection on the end of the unit. Throughout the entire matrix, we've actually got integral tube sheets that support the matrix. I say it's a modular range. It's too difficult to describe in a catalogue. We end up with catalogues that are like 20 millimetres thick. They've got loads and loads of data in them. Best to actually go to selection software to select the product. But we have units that are 1.3 metres, 2.3 metres wide. We have an intermediate unit that's 1600 millimetres wide, single row of fans. On the double unit, we have single row of fans and then an option for a double row of fans. Each of the fan is mounted under a module. Many years ago, we used to just have one module, 1200 millimetres, one fan, that was it. Today, we now have 1200, 1500, 1800 and 2.1 metres. This enables you to actually select a gas cooler to meet your specific requirements. So if you're looking for tremendous energy efficiency, you're going for the D module unit, you have a large amount of fixed surface, minimum number of fans. If you've got a heat exchange matrix that's made of copper, and it's costing you a lot of money, you may want to actually come down to an A module and then have more fans on it. If you need something that's very quiet, you want to reduce the number of fans that you're utilising, you go to a B or a C module. So you can, there's tremendous amount of options that an engineer's actually got now, best described on a computer selection software. Simon talked briefly about the coil being split from the top to the bottom. We have got a lot of experience on steam coils and engine cooling where we're operating at 100, 110 degrees C. And the biggest problem that we've actually found is that, you know, when you're making something that's 7 or 8 metres long, the expansion and contraction that you get on the matrix is tremendous. So we have the split coil, effectively a de-superheater, I suppose, then going into the gas cooler. They're completely separate. The tubes are separate, the fins are separate, and this is to allow for the different expansion and contraction rate that you get on the top of the coil versus the bottom of the coil. And indeed, what we actually do is that we put expansion gaps in the matrix as well. Larger on the top section, smaller on the bottom section, and then what we do is that we support the coil in between with an aluminium tube sheet. You can see on the far photograph, you've got a unit that's being partly built, and the two plates that are sticking up at the top are actually fan baffles. So they actually stop the recirculation, but now they go entirely through the matrix. So you're supporting the coil on every single module that you've actually got. The fan plates have aluminium inserts in them. So every fan plate that goes through that unit on the 1200 through to the 2.1 has got this aluminium plate in there. And the idea there is that as the tube expands and contracts, it's actually sliding on the aluminium. The aluminium is considerably softer than the copper, therefore we're eliminating any possibility of leaks on the matrix. On the larger B modules, C modules and D modules, we have an extra sheet that goes in the middle of the fan plate as well. So across, you know, a 12 metre long unit, you have a coil that's actually supported in 11, 12, 13 places. To further minimise the effect of expansion and contraction, we make the tubes that stick out at the end of the matrix about twice as long as we normally would. And that is really to take the joint away from the fixed point so that any expansion and contraction sideways doesn't actually compromise the joint. Headers, rather boring subject. My wife tells me gas coolers are boring as well, actually, but never mind. We did a number of tests, a number of destruction tests on headers. We looked at mild steel, we looked at K65, we made stainless steel with copper tails, with stainless steel stubs. We were finding that brazing an 8mm diameter tube to a large header, we just got the header too hot, and we rejected K65, although I understand we're now going back to look at it. What we ended up with was a stainless steel header with proprietary caps, stainless steel connections, and then all of the 8mm tubes are actually stainless steel that go into the matrix. We then actually spray it afterwards, but the fact of the matter is that we identified that as a possible corrosion point, so stainless steel is not going to rust in the future. Testing created a little bit of a problem for us. When you're testing at 30, 40 bar, you stick it in a tank, put it underwater, pressurise it, see if you get any bubbles that come off it. Obviously, with the CO2, we've got operating pressures of 120 bar. So we're actually doing a leak test, air underwater, using air with a dew point of minus 30 degrees C, and we pressure test it to 69 bar. looking for any leaks. No leaks, then we then actually put it in a special tank at Searle. We put these yellow header caps over the return bends and the headers, and then we pressurise it up to 170 bar. Like the main fans, like the main unit, you've got loads of different modules. To go with those modules, we have different types of fans. We're using Zeelarbeck, EBM, we're using EC technology, we're using Axitop, the ZA pluses, and we're using Wood's short case axial fans. This is to enable you find that the characteristics of the fans are completely different. These are low pressure, high performance fans. If we can reduce the pressure drop that we impose on the fan, we're going to get substantially more air. So going for a very large module, reduce the pressure drop, and then using this type of fan. And I understand that Simon's just started a project on the flow grids. I'm sure he'll be able to answer your questions on that because I've got no idea what he's talking about. So, finally, I have the product. I've got to go out and sell the product. The best way to actually sell the product used to be a catalogue. Today it's not a catalogue, it's on the internet, it's web, it's computer selection software. So next quarter we plan to actually launch this as a web-based selection software. Fairly simple, all you have to do is put in kilowatt capacity and the ambient. There is an option to put in the noise level, it's not actually displayed on this particular slide. The gas inlet temperature and the pressure, and then your outlet, your desired outlet temperature, and then the minimum and the maximum pressure drop that you actually want through the coil. This is so that you can design for when you go from transcritical to subcritical, you minimise the pressure drop through the coil. Press the button. I won't say it gives you an instant answer, but it's displayed as a series of options. Normally we have 10 options for you to consider. The program automatically selects the most energy efficient, the smallest, and the most competitive. And then it gives you another 7 selections, which are the real selections that you should be looking at. And so you can see from here that it gives you the model. In this particular instance, the yellow highlighted one, GF, which stands for gas flatbed, an MC101. So it's the M module, so it's a single row of fans. C module, 1800 millimeters underneath the fan, and a 101 it's a one row, one fan unit. And it summarises the duty for you, the circuits that you've actually got, the nominal sizes of the unit, and then it goes on to give you a specification sheet. So it's a fairly detailed specification sheet, and then we have a generic drawing that actually goes with it. So once you've actually got this, you've got that, then all you need is the competitive price from us. Okay, no? So, sorry. I think that this project has taken 2 years to come to fruition. It's something that I'm looking forward to selling for the next 5 or 10 years until you actually change it again. GEA, his motto is engineering for a better world, and I think that we've achieved that with this product. Thank you very much.